The Nernst equation is the equation that we can use to calculate E cell, the voltage of a cell, when the cell is non-standard. When we're talking about a non-standard cell, typically what we mean is that the cell has concentrations that are not equal to 1 molar. There are two different versions of the Nernst equation, one using the natural log and one using the log base 10. Whichever equation you use, the non-standard cell voltage is calculated by taking the standard cell voltage, even though it's not a standard cell, and subtracting this correction factor. N in this particular equation is the same N that we've seen in previous equations. This is going to be the number of moles of electrons that are exchanged in the reaction. And then Q, which is a symbol that we haven't seen for quite a while, is calculated like an equilibrium constant K. So it's products over reactants raised to their stoichiometric coefficients. These numbers, 0.0257 and 0.0592, these numbers come from a variety of constants that are built into this equation. If you're curious to know exactly where these equations come from, I'm sure you can easily find the derivation of them in your textbook or anywhere online. And I know that most students don't want to sit through a derivation, so I'm just going to skip that part, and we're just going to go straight to a couple of examples. The first example that we're going to look at is just simply writing the Nernst equation, setting it up. We're not actually going to do any calculations. Using the Nernst equation, really the hardest part is getting the equation set up. And once you get it set up, everything else kind of comes along pretty easily. So I am going to use the natural log version of the equation in this video. And to set up this Nernst equation, first of all, like I said, we're going to need to calculate the standard cell voltage, which is pretty easy to do. We'll practice doing that in the next example anyways. And then we want to subtract 0.0257 volts over the number of electrons that's being exchanged. So this is the first tricky part of the problem. How are we going to figure out the value of N? So we want to look at the problem for some hints. First of all, I'm comparing these two VO chemicals, seeing if it's easy for me to tell how many electrons are being exchanged in this particular process. It's not particularly easy for me, so I'm going to see if I can find something easier. Now I've got some hydrogen. I'm going to see is it kind of easy for me to figure this one out. This one also not particularly easy for me to tell, so I'm going to see if I can find something easier. Iron going to iron 2+. This one is easy. This is one that I can definitely see. It's easy for me to figure out. Iron going to iron 2+ is coming from the loss of 2 electrons. So there is my moles of electrons that are being exchanged. It's 2. And now we want the natural log of Q. So Q, if you recall, is written like an equilibrium expression, products over reactants, each one raised to their stoichiometric coefficient. So we're going to start over here with our products. Our first product is the VO2+, and its stoichiometric coefficient is 2. Our next product is H2O liquid. Remember that we leave out pure liquids and solids, so that won't be included. And then we have Fe2+. With a coefficient of 1. And that's going to be over our reactants. We're going to be leaving out the iron because it's a solid. So we have our VO2 plus with a stoichiometric coefficient of 2. And then we have our H plus with a stoichiometric coefficient of 4. And so this is the Nernst equation. Now again, like I'm saying, we're not going to actually do the calculations on this. We would be able to calculate E cell if we wanted, but in order for us to actually do some calculations here, we would need to be given the concentrations of all 4 of these solutions and plug them into the problem. We're going to look at another example. This next example, in this one we are actually going to be carrying out calculations. Here we're being asked to calculate the concentration of the copper 2+ ion in a zinc copper cell that has a non-standard voltage of 0.8 volts. And we're given the zinc concentration of 2 molar. So this is non-standard, we don't have that standard symbol right there. And we know that it's non-standard because our concentration of zinc is not equal to 1. And then we're also being given the reduction potential for the copper and the zinc half reactions. There's a lot of stuff going on when you're setting up a Nernst equation. So let's just start by writing the Nernst equation so we can just kind of begin to think about all of the different parts that we already know and all of the different parts that we're going to have to calculate or figure out as we put stuff into this problem. And again, I'm going to be using the natural log version of the equation. And we don't know what Q is yet, so I'm just going to keep that as Q. I don't know why I put a 2 there. I mean, I do know why I put a 2 there, but we're going to start with just the N. So first of all, the problem is telling us the value of E cell. So this is a problem where we're not actually calculating the non-standard voltage. We're just, being asked to calculate some other piece of this problem. So we're going to make a note here that the non-standard voltage is 0.8. We do not know the standard voltage for this cell, but it is something that we can figure out. So let's just go ahead and start by figuring out the standard voltage. We'll do that over here. Standard voltage of a cell is calculated by taking the voltage at the cathode minus the voltage at the anode. Cathode minus anode. We've been given both of the voltages for the half reaction, but we don't know which is which. We haven't been given a balanced equation, so we also don't know which is which. The one thing that we do know about the value of E cell is that it's going to be a positive number. E cell is always a positive number for galvanic cells. So what we can do is plug in the two numbers that are provided to us in both different options. So we could say, okay, what if copper is the cathode, so that's going to be 0.337 minus negative 0.763. And then the other option, what if zinc is the anode? Negative 7.63 minus 0.337. It's one of these two options. And again, it's the option that gives us a positive number because the voltage always needs to be positive. So we don't need to actually work the math out on this to tell which one is going to be positive. This is clearly going to be a negative number. A negative minus a negative will be a negative. So this is the correct setup for this equation because it is going to give us a positive E cell. And the only option for E cell is that it has to be a positive number. So we're actually going to get two really important pieces of information out of what we just did right there. The first is just the E cell. I'm going to rewrite it down here. 0.337 minus a negative 0.763. And I will calculate that out. I'm actually going to just kind of scoot it over here. We'll do the math on this. 0.337 minus a negative 0.763 is 1.1 volts. And we'll make a note of that over here that our standard voltage is 1.1 volts. So like I said, not only are we getting the standard voltage out of the cell, we're getting a second really valuable piece of information out of this, out of what we just did right in here. We are determining that the cathode is the half reaction that has the 0.337 volts. So we just figured out that this reaction is taking place at the cathode. And this reaction is taking place at the anode. And again, the reason that we know that is because in order for E cell to give us a positive voltage, we need to set it up 0.337 minus negative 0.763. E cell is always set up as cathode minus anode. So that means the 0.337 needs to be the reaction that's taking place at the cathode, and the negative 0.763 is the reaction that needs to be taking place at the anode. Why do we even care about that? Let me just kind of scoot this out of the way. Well, we know that the cathode, red cat, so cathode, that means that this is going to be the reduction half reaction, and this is going to be the oxidation half reaction. And again, you might be wondering, why do we need to know which is which? Well, we're about to figure it out. In order for us to know N and also Q, we need to write out this reaction. We need to write a chemical equation for this reaction. And the only way that we know how to properly write the chemical reaction is to know which of these is the reduction and which of these is the oxidation. And that's why it's so important for us to have this information right here. Oxidation is a loss of electrons. So the oxidation reaction is the zinc being converted into the zinc 2+ ions. It's losing its electrons. And reduction is gain. So that means the reduction reaction is the copper 2+ ions being converted into copper metal. And this is the balanced equation for this particular reaction. There are two reasons that we really need to know this balanced equation. The first one is solving for the value of N. So we can take a look at these different chemicals here, and we can see that in this redox reaction, the value of N is 2. We're going from zinc to zinc 2+, we're going from copper 2+ to copper. The other thing that we need to figure out is the value of Q. And the only way that we're going to set Q up correctly is if we have a correct balanced equation. Now, one thing that I didn't include when I wrote this out was the states. These metals are always in the solid state, and then we know that these are solutions because we're either given their concentration or asked to figure out their concentration. So Q, the expression for Q, is going to be our product, zinc 2+, over our reactant, copper 2+, and again, we're leaving out zinc and copper because they're both solids. So we have all of that work has been done just to get ready to set up the Nernst equation. We haven't even actually done any of the math on it yet. Let's go ahead and fill these numbers in that we have, and we'll get to work. We have 0.80 volts equal to 1.1 volts minus 0.0257 over 2, and that's 257 volts over 2. We'll just take that off. Times the natural log of the zinc concentration, which the problem tells us is 2 molar, over the copper concentration, which is our unknown. Actually, I'm going to take the molar off there as well. So we now just need to do some math in terms of simplifying. Unfortunately, the variable that we're trying to solve for is at the bottom of a fraction that is part of a natural log. So what I'm going to do is begin by subtracting the 1.1 volts from both sides. I'm just going to kind of try to go a little bit slow with this math because there's a lot of math going on here. So first we're going to get a negative 0.3 volts on the left-hand side. I should have left that volt unit on there. I'm going to put it back. That's equal to negative 0.0257 volts over 2 times the natural log of 2 over the copper 2+ concentration. And now what I'm going to do is divide both sides of the equation by this term, negative 0.0257 over 2. So both sides of the equation are going to get divided by that. So I'm going to take my negative 0.3 divided by negative 0.0257 divided by 2. And that's going to give me 23.35. The volts unit cancel. That's equal to the natural log of 2 over the copper ion concentration. I'm going to move this equation out of the way for us. Now we need to do the inverse natural log of both sides, which is the e function. So e to the 23.35 gives us a huge number, 1.38 times 10 to the, let me count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 to the 10 is equal to 2 over the copper 2+ ion concentration. And now we've got it worked down to a kind of simple problem where we can solve for the copper 2+ concentration. And that is going to be 2 divided by that 1.38 times 10 to the 10 number. 1.45 times 10 to the negative 10 molar. So like I had said, these problems are actually pretty tricky. There's a lot of steps involved in them, and it's most important that you just kind of take your time, have some patience when you're working through these, make sure you have everything in the right order and in the right spot. Double check all of your math. And, just cross your fingers and hope for the best.